In an earlier video, we created a little pressure measuring device made out of a piston and a spring. When we put many of these devices inside a container of liquid, we saw that the spring was compressed more when placed at the bottom of the container of liquid when compared to the top of the container. Our conclusion was then that the pressure inside of a liquid is going to be higher at the bottom than at the top. So, how exactly do we determine the pressure at a particular depth? Let's start by looking at this diagram. In this diagram, we have sectioned out a small column, a cylinder of liquid. It happens to have a depth of D and a surface area of A. Overall, we could say the volume is equal to A times that depth. Now, if we take a look at the forces applied on this cylinder, at the top, we have the force due to the atmospheric pressure. So we'll call that P0 times A. We have the weight of the cylinder itself, mg. And then at the bottom, we have the pressure of the water below this cylinder pushing up. So that's going to be P times A. Now, since this cylinder of water isn't moving, there's no acceleration, the net force of this is going to be 0. So let's go through and look at the net force. We've got mg pointing down plus the atmospheric pressure pointing down minus the pressure due to the liquid below this cylinder. Now if I rearrange this, I can have PA equal to mg plus P naught times A. Again, P naught is the atmospheric pressure. If I divide all of this by A, I have an equation that says pressure is equal to mass over area times G plus the atmospheric pressure. Now we mentioned before that this volume of water, of fluid in this cylinder is equal to the depth times the area. We also know that mass is equal to the density times the volume. Putting these together, we can plug in for mass to be rho, our density of the liquid, times A times D. And then we see that the A's cancel, so it doesn't matter what the surface area is. Now our formula reads, the pressure at a given depth is equal to the density of the fluid times the depth times our gravitational acceleration, G, plus whatever the atmospheric pressure is at the top of that column of fluid. We're going to be able to use this for future problems to be able to figure out what the pressure is at any depth inside of any liquid. Now, based on what we've learned so far, is this figure possible? And if so, how? I'll give you a moment to think about it. All right, so our question was, is this situation possible? The answer is no. A connected liquid in hydrostatic equilibrium, meaning the water is not moving, or the liquid's not moving, rises to the same height in all open regions of the container. Now, why is that? It has to do with the fact that the pressure up above is the same for both of those points. So if you use our formula we just derived, if the atmospheric pressure at both of the open points is the same, then the pressure at a given depth also has to be the same. So our pressure formula also leads us to the conclusion that the pressure is the same at all points on a horizontal line through a connected liquid in hydrostatic equilibrium. So what this is basically saying is that at the same depth, you'll have the same pressure in this particular picture. And if you have a closed container or open container, all of that's going to be accounted for. But you can't have differences in pressure at different horizontal locations. Let's go through and look at some examples to see how this works. In our first example, we have a submarine cruising at a depth of 300 meters. What is the pressure at this depth? We'll give the answer in both pascals and atmospheres. So let's start with our knowns. The depth is 300 meters. The atmospheric pressure is 1 atmosphere, or 101,300 pascals. And we can use our pressure equation to go through and analyze this problem. So the pressure at the depth that we're examining is equal to the atmospheric pressure times the density of the water times G times the depth. If we go and look at our table, we see that the density of the seawater, since this is a submarine, we shouldn't assume that it's in a freshwater lake, we'll assume that it's in the ocean. So the density of the seawater is 1,030 kilograms per meter squared. We can take these pieces and start to plug them into our equation. So again, the atmospheric pressure in pascals plus the density of the seawater times 9.80 meters per second squared times our depth of 300 meters will give us a result of 3.13 times 10 to the 6 pascals. Now again, we convert this to atmospheres, where 1 atmosphere is 1.013 times 10 to the 5 pascals. And that results in 30.9 atmospheres. So as you can see, water has a significant force to it, which means very high pressures at large depths. In our next example, water fills the tube as shown. What is the pressure at the top of the closed tube? So first, let's go through and figure out what the depth is at that horizontal line shown as a dashed line there. So that's going to be the length of the tall tube, 100 centimeters, minus the 40 centimeter height of the closed tube, giving us 60 centimeters. So we know the pressure at these 2 points has to be the same. So if we go through and calculate the pressure at 60 centimeters in the open tube, then we can go through and know what the pressure is at the top of the closed tube. Again, our atmospheric pressure is 1 atmosphere, or 101,300 pascals. We'll use our same equation as before. Pressure is equal to the atmospheric pressure plus density of the liquid times G times the depth. The density of water is 1,000 kilograms per meters cubed. So if we plug these values in, we can calculate a pressure at that horizontal line of 1.072 times 10 to the 5 pascals. This is equivalent to 1.06 atmospheres.